All right. Thanks for this kind introduction. First of all, we are very pleased to present our latest research and the progress we made on the topic of development of an industrial gas burner, mainly for the fuel flexible operation. And if we speak about fuel flexibility, of course, we speak about natural gas and hydrogen for these cases. And in the next slides, we want to present you the groundbreaking combination between additive manufacturing and industrial gas burners, and seeing the additive manufacturing as an enabler to overcome some challenges. So just firstly, a short introduction. This will be a shared presentation together with my co-presenter. And yeah, we are very pleased to present it here. So, this one to switch. This one. Yeah. All right. If we are speaking about industrial gas burners, we also have to speak about the actual application of the gas burner, or where it is implemented. And in this case of our industrial gas burner, we're speaking about the electric arc furnace. And the electric arc furnace already saves about 30% of energy compared to comparable routes, and already saves about 80% CO2 compared to other routes. However, even if the most of the energy is transferred to the furnace by electricity, we still have some requirements for chemical energy just to address cold spots in the melting surface. So that's our use case for our burner injection system. So, and of course, our burner injection system currently is running on natural gas, but with the goal of CO2 neutrality, we have to substitute these hydrocarbons with hydrogen as most promising fuel. So, however, the implementation of hydrogen just is accompanied with some challenges regarding, first one, safety. So we have probability of an unintended ignition, which is favored by hydrogen combustion. Regarding material, we have a higher risk of hydrogen embrittlement in our burner. And regarding our process capability, due to the 3.3 times changed density, we also have changed volumetric flows. So we have a lot of different challenges we had to overcome in our process. So in our process, we started with the conventional burner design. You can see on the left side, it's conventionally manufactured with different components. And we're using this conventional design as starting point, together with the requirements the industrial gas burner has to fulfill in the application, and started our iterative loop for this development. The first point was the optimization and design of a new burner, which is more compact and manufacturable by additive processes. This is followed by the actual additive manufacturing of these burners, which is followed by more or less parallel investigation of the burner and the combustion behavior by experimental studies and simulations. And running this loop, we were able to derive a fuel flexible optimized burner. We just conducted several tests to get an idea of the combustion behavior. And with the long-term goal, we also included in the design is just like to have a full scalability from the scale from laboratory tests, which ranges from 50 to 500 kilowatts, up to the real megawatt scale the burner has to have in the electric arc furnace. So, speaking about the electric arc furnace and the real application, the burner injection system has 3 different modes which it has to fulfill. This is the shrouding mode, the burner mode, and the injection mode. And in the first instance, we see that in the burner is mainly affected by the harsh conditions in the electric arc furnace. So we have hot metals in there. We have just mechanical wear, which is comes from the metals, and we also have a high thermal load from the electric arc furnace, because we have temperatures over 2000 kelvins. So these are the effects of the furnace on the burner. However, we also have very high requirements for the combustion, and we have different modes and affections mainly for the thermal wear. So we have internal combustion zones, mainly in the shrouding and in the injection mode. So we have very high temperatures inside of the burner. And in the burning mode, we have a flame which is close to the burner tip or even at the burner tip. So we have a high thermal impact on the one side from direct heat transfers, but also from radiation. So in our design process, we had to overcome these challenges on the one side by sufficient or suitable material selection, but also by the implementation of sufficient water cooling by cooling jackets. So the other requirements are mainly focusing on the application requirements. So, for example, in the shrouding mode, we have a demand for a very high outlet velocity. For the injection mode, we have the requirement for a very long jet, the oxygen jet. And especially for the burning mode, which is the most affected one by the fuel switch, we have to prove that we have a stable combustion without any instabilities or flashbacks or burner damaging. So we overcome this by implementing complex gas and cooling channels. And also regarding the stability and the forming of the flame, we also implemented very fine gas channels, which were only able to manufacture by additive manufacturing processes in these cases. So, as I already said, these are the preliminary investigations. We already conducted a test in an atmospheric test rig, which are shown here. On the left-hand side, you can see the operation or the free flame test for the natural gas operation, and on the right side for the hydrogen operation. And we clearly see that we have a very stable flame in both cases over the whole fuel flexible range. We have no instabilities, no flashbacks, which is very good. We have some changes in the flame actually. So we, for the natural gas flame, we have a lifted one, which is more favorable for in regard of the thermal wear of the burner. However, we see that we have a shorter flame for natural gas case, but also a broader flame, so a more compact one, sitting closer to the burner. And for the hydrogen case, the flame is more extended. We have a longer flame, but also a thinner flame at the same time. And even if you can see in the middle, the flame for the hydrogen case is sitting at the burner tip. We had no thermal wear, and this proved that the water cooling was sufficient, and also the material selection provided us a manufactured or processed material which was able to have, or with a high thermal conductivity, to transport the heat from the burner tip to the water cooling channels. Yeah, I would hand over to my co-presenter.
Yeah, thank you, Christian. So we have seen like all these design freedom we have in additive manufacturing. We can really address all the challenges there for combustion and especially for hydrogen combustion, including the complex structures for cooling, for gas ducts, but also enhance improvements in safety issues in flame stability and also emission on emission points. But what we cannot really see is also on a beneficial point is even from economic side is that we have a quite compact design where all the geometric features from the burner are integrated in this compact design. So conventionally, these burners are assembled and welded together from above 40 parts, and there we don't count any screws, we don't count any seals. So we can streamline all these manufacturing steps within one additive manufacturing step. And yeah, also we can really reduce the material with this AM design, which is not only economic and ecologic beneficial, but also really reduce the manufacturing time within additive manufacturing. Yes, and one challenge also Christian mentioned was like the really high thermal loads we have on these burners when we use them in an electric arc furnace. And so the concept is to address this thermal loads is a cooling concept within our burners, but this therefore we need a material with really high thermal conductivity. And then, of course, the material of choice would be copper. And I guess most of you might know the challenges in processing copper with infrared laser because of the high thermal conductivity and the low absorption rate of the infrared radiation. There are some solutions on the market which we couldn't use, unfortunately. For example, we didn't have a green laser, and we didn't have a laser above 1 megawatt at the beginning of our project. And also other copper alloys were not a suitable solution for us because, for example, alloys like copper, chrome, zirconium has only thermal conductivity of 70% of pure copper, which was not enough for our application. But then, fortunately, we crossed ways with this guy mentioned here, Mr. Hurt. He developed a surface-modified powder, which we can process with infrared radiation at a power below 400 watt with his improved surface modification. And yeah, there we had like a pure copper material of above 99.5% pure copper, where we can achieve with the right heat treatment a thermal conductivity above 360 watt per meter Kelvin, which is equivalent to 90% AICS electric conductivity. And yeah, this was the first generation of this copper powder, but yeah, development is going on. So at the newest generation, there is the oxygen content is 50% less, and also the absorption of this material is even higher, so that the process stability is even better, and also we can increase the build-up rates there. Yeah, and with this powder we could achieve we could build up this burner, which we have tested, as you have seen at the previous slide from Christian. And there, yeah, to achieve or to build up these burners, we went through like really well-known process development processes. So first we made we developed the parameters for hedge and contour exposure. The goal here, of course, was high or a relative density up to 100%. But this was not only the only goal. The other one comes from the requirement of the burner, so the really high thermal conductivity. So what we did is also experimented with different heat treatment strategies, then measured electric conductivity and calculated the thermal conductivity. And when we have seen, okay, we have achieved our goal there, we decided, okay, we can use this powder for our project, and then kept on with the process development with upskin, downskin, process parameter development, and also scanning strategy for large surfaces. So this was like really quick went through this process development, and so we achieved manufacturing this burner. One thing I also want to highlight here is a relatively low surface roughness compared to other copper PBF processes or other copper PBF materials, which is also really beneficial for our fluid application there at the burners. Yeah, so this is from a project which will end at October next year, and within this project, yeah, we could show that we can combust our burners with natural gas and also hydrogen at the same time. So we reached this goal, but also there we've seen some new challenges. Yeah, Christian has already showed, and also here on the left side of this slide you can see the flame behavior is quite different, the flame characteristics. And this is something we want to address at the second phase of this project, which we want to continue in October next year. There we want to extend our project from the lab scale to the application scale, and the goal here is to develop an inverse design concept, or like this we already started, but we want to improve this concept to replace the natural gas burners with our hydrogen burners quite easily. With this inverse design concept, we want to modify our flame characteristic, especially for our application, so that we can, as I said, remove the burner in the application quite easily, and so accelerate the transformation from natural gas to hydrogen in this step. And this is like one overview about the project, what we have done, what we plan to do. Thank you very much for your attention, and we're free for questions.
Thanks.